Now let's welcome our speaker, George Nasr from University of Nebraska-Lincoln, who will tell us about a combinatorial formula for Kazhdan-Lusztig polynomials of sparse paving matroid.
Yeah, thanks. Thanks. Thanks the organizers for having me and for all of you for attending my talk. Just a quick comment. I've given this talk twice now, once at the GSCC seminar in like August and once at Combinatorial a couple months, 1.5 months ago or so. So there is one tiny new thing towards the end of the talk that I may have time to slip in that I've done since then, but otherwise it's mostly the same. My talk today is about these polynomials called Kazhdan-Lusztig polynomials, but I am studying them in a context that is very different from how they were originally defined. So I do want to take a little bit of time to talk about the classical theory, which will allow me to more naturally segue into the theory that the context for which I study these polynomials, which is for matroids. And I'm not going to expect people know what matroids are, so I will give a brief background on that as well in this talk. And once we know all about what these polynomials look like, or things about these polynomials for matroids, I'll talk about some of my results, which involves showing a combinatorial formula for a special collection of them. So let's get started. So some context and background. In 1979, Kazhdan and Lusztig give a recursive definition for a polynomial. Now, this polynomial was associated to a pair of elements of a group called the Coxeter group. And many years later, this starts getting called the Kazhdan-Lusztig polynomial. And in their 1979 paper, Kazhdan and Lusztig proved that for a special case of Coxeter groups called Weil groups, these polynomials always had positive integer coefficients. These polynomials always have integer coefficients, but they actually showed that they were positive. So they conjectured, and Elias and Williamson 35 years later proved that all of the coefficients are non-negative for any Coxeter group for any pair of elements. So this was cool. Before this, though, some combinatorial interpretations kind of helped lead to non-recursive definitions for these polynomials. And the reason that this is really useful and important is that, you know, if you're trying to get some intuition for these polynomials, you want to be able to write these down, and recursive things are hard to compute. So these two things, this combinatorial interpretation and non-negativity, have kind of elevated to become motifs in what is now the more general theory of Kazhdan-Lusztig polynomials, which was made in part possible by Richard Stanley. So basically, Richard Stanley was studying these polynomials, and the definition for the polynomials is not only recursive, but it actually specifically depends on a poset structure you can put on this Coxeter group. It's called the Bruhat order. And Stanley realized, like, there's nothing special about the Coxeter group. You just need a meaningful poset structure, and you can define a Kazhdan-Lusztig polynomial for any object. And so one different object that we can define a natural poset for is a matroid. So let's talk a bit about matroids. So there are plenty of and lots of definitions of matroids. If you haven't seen these before, I'm going to give one that will make my talk the most smooth. I'll start with a finite set E, a non-negative integer D, and these collection of D subsets of script of E, which I will call script B. And this collection satisfies two conditions. The collection is non-empty, and this one's very lengthy and long, but the idea is for any pair of elements in this script B, I can remove something from one, add something from the other, and still get another member of script B. So it kind of gives you a way of exchanging elements between members and getting a new member. So the pair of E and script B is called a matroid. The ground set of of the matroid M is what we'll call this set E. And each element of script B will be called a basis. So this B and B prime in statement 2 are bases for the matroid. And any subset of a member of script B, any subset of a basis is called an independent set. And at this point, you're kind of like bases, independent sets, linear algebra, right? And that is right. One of the most classical examples of a matroid is coming from straight out of linear algebra. You take your ground set to be the columns of your matrix, and you let script I, so I'm defining this new set called script I to be the linearly independent collection of columns. And if you take your maximal sets to be your bases with respect to inclusion, you can use that pair E and B to build a matroid, and we call it a representable matroid. And if you look back at statement 2 here, this is just a fact about bases in a vector for the same vector space, that you can kind of move elements around and get another basis for your vector space. But this wasn't the only thing that led to the definition of a matroid. There was a recognition that graphs have very similar properties in their structure as independent sets do in vector spaces. And I know there's lots of graph theory at this conference, so I thought I should include. You can take your ground set to be the edges of a graph, and your bases to be the acyclic spanning collection of edges. And that also gives rise to a matroid. It's called a graphic matroid. Cool. So these two matroids have really nice ways of thinking about them. The representable things have matrices. The graphic matroids have graphs. I want to introduce the matroid that I will care the most about in this talk, but it doesn't have some nice thing associated to it. But it is not too bad to define. So what you do is you define your collection of bases to have the property so that any pair of D subsets that are not a basis, the cardinality of their symmetric difference is at least 4. So all we need to satisfy is this loose condition. They don't all have to have the same cardinality. They just need to all have cardinality at least 4. So that is enough to guarantee a matroid, and we call these sparse paving. In the special case where you take all possible D subsets to be a basis, that is, if every D subset of E is a basis, we get what's called a uniform matroid. And so why do I care about these sparse paving matroids? Why are they in the title of my talk? Well, personally, it's because I proved something for a collection of matroids and they happened to be sparse paving. It was purely coincidental. I wasn't specifically looking for these matroids. But there is a stronger reason to care about these matroids from like a research perspective, because it's actually conjectured that pretty much every matroid is sparse paving. More precisely, if you take that ratio, that fraction you see there, the number of sparse paving matroids on n elements and the number of matroids on n elements, and you take n to infinity, we conjecture that that equals 1. And it's already known when you insert a log in the front of those, or precompose or whatever. So it is known in a logarithmic way, but it's still open whether it's just true straight up in general. And it's believed to be true, at least I think so. So yeah, that's some background on matroids. And now I feel like we can talk a little bit more about what the Kazhdan-Lusztig theory looks like for matroids. So in 2016, Elias, Proudfoot, and Wakefield defined these Kazhdan-Lusztig polynomials for matroids. And so if you might remember at the beginning of my talk, I mentioned that Stanley said you can define one of these polynomials for any object as long as you have this meaningful poset. In the Coxeter group case, that was the Bruhat order. For the matroid, it's called the lattice of flats. I won't be talking about what flats are, but I can talk about those after the talk if people want to know more. So these three authors, just like Kazhdan and Lusztig, conjectured that their polynomial was non-negative, proving it in the case where the matroid is representable, those matroids that correspond to matrices. And very recently in October, which I guess it's already been 6 months-ish, man, COVID time, they proved that the conjecture holds for all matroids, which is really, really awesome. But if you remember, again, back to that first slide, I mentioned there were two motifs in the kind of this study of Kazhdan-Lusztig theory. There is this like non-negativity, which is done, and also this combinatorial side of it. Do these coefficients mean something? Do they count something? And this theorem, while remarkable that it could be proven, relied heavily on algebraic geometric methods and did not provide any combinatorial insights. And so I'd like to show some combinatorial insights I've had in the case of sparse paving matroids. So let's talk about some combinatorics. So I've got some skew-shaped tableau here. And so just to make things easy, I've kind of defined my own parameterization of these tableau. So you have a column on over here, you've got a column of A, I-1 columns of 2, and then a column of B boxes. And we're gonna fill these in the standard Young tableau way where you use the numbers 1 through the number of boxes, and you arrange the numbers so that the rows increase left to right and the columns increase top to bottom. So all of those fillings I'll denote as SKYTE, skew Young tableau of AIB. And in the special case where I fix the position of 1 to be this corner, we'll call that SKYTE bar of AIB. Note that the only other position where 1 can appear is at the top of this right column because of that increasing behavior or condition. Okay, and so this is all I actually need to, oh yeah, let me give at least one example of some fillings just to, I feel like it's helpful. Note that the one on the left would not be a member of SKYTE bar of 435 because of the position of the 1. Okay, so I'm ready to state my main result. I will remark at this point, I have not shown you the definition of Kazhdan-Lusztig polynomials. It's mostly because even in a 50-minute talk, I found that I couldn't give an enlightening description of those polynomials. So I will just show you what my result says. Here is a reminder of what a sparse paving matroid is. And here is the main result. If you take M to be a sparse paving matroid, I'm going to let this parameter rho be the number of D subsets that are not bases, and I'll let M be the size of the ground set minus the size of any bases. Then the ith coefficient of these Kazhdan-Lusztig polynomials is given by this expression, where this lowercase s here corresponds to the cardinality of that set that we've seen on the previous slides. So, you know, even if this looks like just a bunch of noise, a couple remarkable things about this. First, note that what we're subtracting does not depend on M at all. I can let that ground set size get really, really big, and all that's going to change is this first term. That's kind of cool. Also, remember the condition on sparse paving matroids just says the symmetric difference of your two sets has to be of two non-bases of size D is at least 4. But you can have some of size 4, some of size 6, some of size 10. I don't care how chaotic that looks. All that ends up changing the matroid is the number of sets. Or all that changes the formula is the number of sets that are not bases. So it doesn't actually care about what the structure of the bases look like and corresponding to intersections and stuff. It just cares how many aren't bases. And of course, this formula is positive because we know all these polynomials are positive now, but I had proven this before that result came out, so yeah. One thing I will say is if you let rho be 0, that means B is all the D subsets of E. That's the uniform case, and then you have a really nice manifestly positive interpretation for your tableau. It's just these skew-Young tableaus. And I do have another really nice interpretation, but with about 20 seconds left, I'll instead just jump to my last slide just so you can see some of my future directions. I will explicitly comment that I have recently had success generalizing to matroids that correspond to Skype bar of A stuff as opposed to just a 2. So on that previous slide, I had a 2 right here, and I now know how to just put an A there. So I'll go ahead and stop there. Thanks all for listening.
Let's thank George for the great talk. So if you can unmute yourself, we can hear some real clapping, or I can type clap in the chat. So now it's for questions. So there is a chat. Stefan asked, how does one come up with such a formula? I think he referred to your last combinatorial formulas.
Yeah, thank you for asking a very important question. How does one? So the way this actually happened is, you might remember I just remarked that if rho is 0, that corresponds to the uniform case. So that's actually right here. If all of your D subsets are bases, this is the formula. I actually discovered this one first. And how that one got discovered is my advisor noticed a different object, some strings, seem to be being described by some recursive formulas we found in the original paper. And it turned out that those strings are in bijection to these tableaux. So it started with like an initial observation. And then I was like, okay, can I just delete one basis and figure out what happens there? And I was able to prove that. And then it turned out that it didn't matter how many bases I deleted, so long as I'm saying deleting bases like starting from the uniform matroid. So I have the uniform, I pluck out a basis, and I figured out that it was this value just from a lot of sage computation. And I was like, what happens when I remove 2? And it just happened to be 2 times that. So a clever observation from an advisor plus a lot of luck with computations.
Really nice. Thank you.
Yeah. That was a little rambly, but yeah.
Would your result hold if you didn't have a sparse paving matroid as well, or is that really essential in the proof of your theorem?
So just to clarify, do you mean like if I didn't have this condition here? Yeah, so if you lose this condition, then a lot of the structure that I leverage in the proof of the matroid no longer holds. That condition guarantees some like nice things are happening in the like independent set structure of the post set, or I'm sorry, of the matroid. So I really need that to be able to leverage it. However, I do conjecture that based on my success generalizing to Skype bar of AI d minus 2y plus 1, which these matroids are not sparse paving, I do conjecture that we may be able to use Tableau to describe all these matroids, but for that specific formula, you really need to have that condition on the symmetric difference.
Yeah, really nice.
I think we have time for one more question. Does anyone want to unmute and ask?
Could I ask, so it seems like you're saying that you have a combinatorial interpretation for basically almost all matroids, and then you also showed it for uniform matroids prior to this. What's there left to show a combinatorial formula for?
Oh, I mean, already like these matroids that I am referring to here are already not sparse paving or uniform. I mean, this condition, even though there are, just to clarify, it's only conjectured that sparse paving are almost all. We know it when there's a logarithmic there. So, but you know, obviously almost all does not mean all. There are a lot of weird cases that you can talk about. And so like what ifs, you can allow some symmetric differences to be 2, but they're not as easy to understand. So we have to introduce some symmetric differences being 2 now and try to understand what happens when some of these are 2. And that's all of those cases are completely valid. And I'm trying to avoid introducing more Matroid theory language, which is why I'm being vague. But I can talk a little bit more in detail about how, you know, there are lots of cases where this can be too, and we need to be able to take care of all of those cases as well, not just when there are at least 4.
Great. Let's thank George again for the great talk.
Thanks, everyone.